Welcome to the fastest way to learn data structures and algorithms. Today, we are mastering LeetCode 155, the min stack. This is a fundamental design problem that tests your ability to optimize data retrieval beyond basic stack operations. Let's look at the problem statement. Our goal is to design a stack that supports all the standard operations, push, pop, and top, but with a twist. We must also be able to retrieve the minimum element in the stack, in constant time, or O of 1. Standard stacks don't track the minimum, so we need a clever way to keep it updated as the stack grows and shrinks. Imagine a specialized filing cabinet. Every time you drop a new file into the drawer, you also attach a small min tag to that file. This tag doesn't just show the file's value, it shows the smallest value in the entire drawer at the moment the file was added. Even if you add or remove files later, that tag remains a snapshot of the minimum at that specific depth. To find the current minimum, you just look at the tag on the very top file. Our strategy is to use two stacks working in perfect harmony. One is the main stack, which stores our actual values. The second is the min stack, which acts as our min tag tracker. Every time we push a value onto the main stack, we look at the current top of the min stack, compare it with our new value, and push the smaller of the two onto the min stack. This ensures the min stack's top always reflects the minimum of everything currently in the drawer. Let's dive into the dry run. Look at the screen. We have our main stack on the left and our min stack on the right. First, we push 3. 3 goes onto the main stack. Since the min stack is empty, 3 is also our current minimum, so we push it onto the min stack as well. Next, we push 5. 5 goes onto the main stack. We compare 5 with the current min, which is 3. 3 is smaller, so we push another 3 onto the min stack. This tells us that even with 5 on top, 3 is still the smallest value in the stack. Now, we push 2. 2 goes onto the main stack. We compare 2 with the current min, 3. 2 is smaller, so we push 2 onto the min stack. Our current minimum is now 2. If we call getMin, we just look at the top of the min stack, and there it is, 2. What if we pop? We remove 2 from the main stack, and we must also remove its corresponding min tag from the min stack. Now, if we call getMin again, we look at the new top of the min stack, which is 3. The minimum correctly reverted back to 3. Now, let's look at the Python code. In our constructor, we initialize two empty lists, stack and min stack. In the push method, we append the value to the main stack. For the min stack, if it's empty, we just append the value. Otherwise, we append the minimum of the current value and the current top of the min stack. The pop, top, and getMin methods are straightforward, we just perform the corresponding operation on the stacks. Because we pre-calculated the minimum during the push, getMin is a simple O of 1 retrieval. Looking at the complexity, the time complexity for every operation is O of 1. We never have to search through the stack to find the minimum. The space complexity is O of n, because we are using an extra stack to store the minimum values. And that is the min stack challenge mastered. Save this video for your next system design or data structures interview, and follow Leo Academy for more premium DSA guides.